Well, welcome back, guys. Had a little bit of a challenge here for a second. Okay, I'm working now. Hope everyone's doing okay. Had an extra week of vacation. I'm assuming everybody is back online. If not, let me know. Shoot me an email if you're having trouble getting into your email and getting into Canvas, and we'll see what we can do to get that fixed. So anyway, as you know, everything has been pushed up for a week. So everything's been moved forward. Today's, and myself, I have not been able to get access myself until late. I have a ton of things to grade. So I haven't had a chance to catch up on those. They're coming. I should get them done here in a couple of days. Today is that exam that we would have had normally a week ago, covering chapters 7 through 9. It is open until 10 p.m. tonight. So when you get a chance, don't forget about it. Knock it out as soon as you can. All right. Any questions, comments at this point in time? Okay, because my plan is we ended up on, which we haven't started it, but I was going to start with chapter 10. Okay. Anybody have any comments, questions, concerns? All right. Well, let me pull up chapter 10. All right. Chapter 10 deals with chemical reactions and types of chemical reactions. A couple I kind of introduced to you when previous chapters. I talked about neutralization reaction when we were talking about the acid base chapter. Okay, combustion reaction. It's another one that we all do every day when we use our vehicle. We are combusting a hydrocarbon. Anyway, the point here is that of all the chemical processes that occur, there are only 6 types of reactions, and we're gonna talk about each one. 6 types, that's all. And along the lines of that, we're gonna talk about how to balance chemical reactions. Now, why is it that we're balancing chemical reactions? Well, that's because one of the basic laws of physics and chemistry, and that is the law of conservation of matter. That matter is neither destroyed or created. We are, in effect, just taking the matter that we have and put it into another form. Okay. And so if we take carbon, for example, and carbon's in the form of, let's say, some vegetable, it could be tissue, and that carbon, we ingest it. Then we process it. That same carbon, which has 6 protons, is now incorporated into our body in some form. It could be in the form of also tissue or cells or anything. Okay. And during our process of metabolism, eventually maybe that carbon gets converted back to, let's say, carbon dioxide, which as we all know, we exhale. And so that carbon that was started off on, let's say, on some vegetable or a piece of meat, we ingest it, gets converted into our system, we metabolize it, then we exhale it now in the form of carbon dioxide. It's still carbon. It's in a different form, but now it's out there in the air again, and then maybe gets absorbed again by another plant life, and gets incorporated into its system. And then the process, just the cycle of the atoms, if you will. The point is this: the total mass of reactants will equal the total mass of the product. So if I start off with 10 grams of reactants, whatever reactants that may be, I'm going to end up with 10 grams of products. In different forms, but 10 grams total, okay? And if I start, for example, in this example, 254 carbon atoms is an arbitrary number. But you could, if I start off with 10 billion carbon atoms as reactants, then at the end, after it's done doing whatever it's doing, I should have 10 billion carbon atoms, in this case, 254. And that is what we mean by the conservation of matter, okay? And we have to take that and we put it into the reactions so we balance them. Because if I start off with 10 carbon atoms in the reactant, then I'm going to end up with 10 carbons as a product. It could be distributed amongst the different products, but I'm going to have a total of 10 atoms. Okay. And this is what we call a balanced chemical reaction. Now, balancing chemical reactions are crucial. Normally, a lot of times the reactants is a simple 1-to-1. I got one reactant A and one product and one reactant B. They react, something happens, and they make a product AB, for example, 1. But sometimes we get a 1-to-2 ratio. Sometimes we get a 2-to-3 ratio. It could be a 4 or 5 ratio. It can vary depending on what the reactions are. But these ratios is what we're going to use in our calculations when we eventually get to that point of being able to calculate how much reactant we need if we need an X amount of product. Okay. And whether we do that reaction in the lab with a few milligrams of material is true whether we do it a few milligrams or whether we do it with tons of material out in some industrial plant. That same ratio is true for both small scale and large scale. All right, so balancing chemical reactions, first you always write a chemical reaction, making sure the chemical formulas are correct. And we started that, refresh your memory, how we were taking ions together to make chemical formulas and making sure that we add them up in the correct ratio of plus and negative charges, okay? Because they're going to add up to give us a 0 charge for these ions. So we need to learn, refresh your memory on how to put the chemical reactions or the chemicals together in the proper ratio, okay? Then once we do that, after we do that, because we're going to be given, we're given the reactants, we'll be given the products, or we're going to determine what the products are from a chemical standpoint. Then we come back and we balance chemical reactions. Now, some of these chemical reactions that we're going to work with, the balancing, that means we add up to make sure we got the same number of atoms as reactants and the same number of the same atoms as products. That's balancing. If I got 10 carbons as reactants, I'm going to have 10 carbons as a product. If I got 30 hydrogens as reactants, I need 30 hydrogens as products in that manner. And so that's what we're going to do about balancing it. Some of these processes of balancing a chemical reaction, unfortunately, are basically a trial and error. So you put a number, a coefficient, and we'll get some examples, and say, okay, let's try 2 here and see how that works. And we start off reactants and then move over to the products and put a number there. And we go back and forth until everything's balanced. So a lot of them are like that. There are some, however, that we can be more systematic and have a more specific example on how to balance it, okay? And we'll talk about those when we get to them. So some are trial and error, some have a very specific stepwise in how to balance your chemical reaction. Okay, so when we balance, we put the number, not the subscript, but the number up front. That's the coefficient. Now, once the subscript is set, we don't change that. That stays on, that's etched in stone, so to speak. It's a coefficient. We can change to any number that we need just to get things balanced. So we can change the coefficient as many times as necessary. All right, for example, let's take this reaction here. We have, let's first put it in words of what the reaction is. Okay, because you could have a question where you're given the reaction in words, and from the words, you need to convert it to a chemical reaction. So in this one, it says, that hydrogen gas in the presence of oxygen reacted to create water, H2O. Okay. All right. So once we write that down, hydrogen gas, because we know it's diatomic, so it's H2. And oxygen gas, we also know it's diatomic. Remember, have no fear of ice cold beverage. Those are the diatomic elements, I should say. Reacts to give us H2O or water. Okay. Now, we balance it by putting the coefficients in front of the oxygen. So let's do this. Let me rewrite that equation. Let me draw it and say, all right. We have hydrogen gas plus oxygen react to give us water, H2O. Okay. So once we write that down, now we come and balance it. So we look to see now the reaction given to you on the PowerPoint, it's already balanced, but let's go through the step of balancing this. And so we can see we got two hydrogens here, okay, and two hydrogens as reactants and two hydrogens as products. Oxygens, we got two as reactants, but only one as product, one in the form of Anybody had a question?
Go, don't be.
Okay. All right. And so you can see we got one oxygen here and two as reactants. So we need to balance it. And so what if we put a 2 here? If we put a 2 in front of water, that does balance the oxygens because we have two molecules now, H2O, okay? And then what happens to the hydrogen? The hydrogen goes up in number to 4. Okay, so now we have two oxygens, 4 hydrogens. Okay, the oxygens are balanced, but the hydrogens are not now. So what we do is we put a 2 in front of hydrogen. Now we have four hydrogens as reactants, 4 hydrogens as products, 2 oxygens as reactants, and 2 as oxygens as products in different forms, mind you, but it's still oxygen. That oxygen with 8 protons in the form of diatomic oxygen is the same oxygen in the form of water. It's still got 8 protons, okay? Electrons were tossed around, okay, created something new here, but that's what I mean, that we have satisfied Mother Nature in the fact that we had not created or destroyed the atoms, we just put them in different forms. All right, so what we have now is a balanced chemical reaction. What this means now is this, look at the ratio. Let me clear this up a little bit. That means that for this reaction to occur, I need 2 molecules of hydrogen and only 1 molecule of oxygen, okay? And when that reaction occurs, I end up with 2 molecules of H2O. And my ratio there is 2 to 1 with respect to hydrogen to oxygen. Okay, 2 to 1. The ratio between oxygen and water is a 1 because it's understood, even though there's not a 1 there, it's understood to be a 1. 1 oxygen, 2 waters is that ratio. And so here you can see you have 4 hydrogens total in the form of hydrogen gas, the gray given by the gray color series. 2 oxygens given by the white color ones in the form of oxygen. And now we still have oxygen, but now they're in the form of water. They've been broken up. The diatomic oxygens are broken up. And then the hydrogens have combined with it to form H2O. So you can see we got a balanced chemical reaction here. Okay. And we put a 2, we use coefficients because obviously we're not going to write. We're not going to, oh, sorry about that. We're not going to write the 2 molecules here. So that's why we put the coefficients there up front. All right. Let's look at this one. So here, not to worry about the reaction here, but I think we've talked about these chemicals already before. We got nitrogen, a diatomic gas, hydrogen gas, and NH3. If you recall from our Lewis dot structures, that is a formula of ammonia. And so nitrogen gas in the presence of hydrogen gas reacts to give you ammonia, NH3. All right, so notice here we got to balance it. So we got 2 nitrogens on the left as reactants, 2 hydrogens on the left as reactants. But as products, you can see that we have 3 hydrogens. Okay, so things are not balanced. So we got to balance them. Now, the simplest thing we can do, hopefully you can recognize that. Remember when we were putting formulas together when we had a +2 and let's say a +3 and a -2 ions, and we're putting them together, we were looking for a common factor. You can use that same technique here. See, I got 3 hydrogens here, but 2 hydrogens here. So what if I put 3 there and put 2 there? Wouldn't that balance my hydrogens? It certainly would, because my common number is 6. And so I got 6 hydrogens as reactants and 6 as products. That boots up my nitrogen, not count to 2, but that's okay because nitrogen is diatomic and I got 2 nitrogens. So by default, the nitrogen automatically balances out. Okay. Let me restate that here. So I'm looking at I got 2 hydrogens sitting here and 3 here. I use a common number of 6, so that means I can put a 3 there and I put a 2 here. Okay, and that balances out. Okay, 3 there, and I got balanced chemical reaction. Now you can see, give me 1 second, please. Okay, I'm back. And so we have a balance. Look at the ratio now. I got a 1-to-3 ratio between nitrogen gas and hydrogen gas. That's that 1-to-3 ratio. Now, why is that of interest? I'm going to tell you why. Okay, remember way back when we were doing conversion factors? It's back, okay? And I stated back then that we needed to learn to use these ratios. Now, way back when, remember I said 1 inch was equal to 2.54 centimeters, okay? And then I said, well, here you go. You can put 2.54 centimeters in the numerator, 1 inch in the bottom, or the other way around, okay? Remember all that? Okay, well, here's the same technique because, let me change the color here so we don't get contrast. I got 3 there, 3-to-1. Remember, it's understood to be a 1 here, okay? So I have a ratio of 1 nitrogen to 3 hydrogen gas. And I can write that either in that manner with hydrogen in the numerator and nitrogen in the denominator, okay? So that is the relationship between the hydrogen and the nitrogen. But I can have a relationship between the nitrogen and ammonia. Okay, which says that 1 nitrogen per 2 ammonia. And again, I can write it like that, or ammonia in the numerator. Okay. What other relationship do I have here? Let me change the color a little bit so we can keep things separate. We have the relationship between hydrogen and ammonia. Okay, where we have 3 hydrogens per 2 ammonia. Okay, or I can write it with the 2 ammonia and the 3 hydrogens. And so this hydrogens, this is H2. So in this simple reaction with 2 reactants and the products, I have 6 conversion factors that relate the reactants with each other and the reactants with the products. And those ratios I can utilize to do my calculations, okay? They're going to be just like when we were doing these problems down here, and I said, depending on which one you select, depends on the question and your units and keeping track of your units. All right, if I'm looking for centimeters, then I use this one from inches to centimeters. If I started off with centimeters, I need inches, I use that one. Remember that part? Well, here I am over here now with these conversion factors. And my question, if I looking for nitrogen with respect to hydrogen, I use that one and vice versa, okay? Because why? Let me clear, it's got a little messy here. Because it could be, for example, if I need 10 grams of ammonia, how many grams, that's supposed to be a question mark. How many grams of hydrogen would I need to make 10 grams of ammonia, or vice versa? If I have 10 grams of hydrogen, how many grams of ammonia am I going to make? And I'm going to need those coefficients from the balanced chemical reaction to be able to answer that question. So that's why balancing the equation is very important, because if they're not balanced properly and you just leave it as a 1 to 1, then your answer would be incorrect, because the ratio between hydrogen and ammonia in this case is 3 to 2, right here, 3 to 2 ratio. All right, so it's all tied in here. So with respect to calculations. All right, let's take a look at this one. We have hydrogen, okay, and bromine to give us HBr. Now, again, these type of reactions are a trial and error as far as balancing them, okay? So in this case, HH2, Br2, I can very simply just put a 2 in front of HBr, and guess what? Everybody's balanced. And then I recognize my ratio between hydrogen and bromine. It's a 1 to 1. Between hydrogen and HBr is a 1 to 2. Between bromine and HBr is a 1 to 2. Okay. All right. There we go. Here we got carbon monoxide. Notice the in the presence of carbon monoxide and oxygen, the reaction proceeds to give you carbon dioxide. So that's the words that you put them into a formula. Carbon monoxide plus oxygen gives you carbon dioxide. Now to balance this, a little bit more challenging, but if I put, because I got 3 oxygens on the left-hand side and I got 2 on the right-hand side, the carbon is balanced, okay? Well, maybe if I look for an even number, if I put 2 in front of carbon dioxide, it gives me 4 oxygens, but my carbon goes up, okay? So I need a 2 in front of carbon monoxide to give us 2 carbons, which by default now gives you a total of 4 oxygens, 2 in the form of carbon monoxide and 2 in the form of oxygen. Okay. All right. So this is why I was stating to why I was giving you the reaction in words, because we're going to start writing reaction from words. Okay. And remember the physical states: solid, liquid, gas, and aqueous. You know, how do we know it's solid, liquid, gas? Well, remember that chapter? We had a whole slide. Now, you know, there's only, of all the elements, there's only 2 liquids, right? Okay. And there's a X number of gases, and everything else is the following. So, and then aqueous, normally those are ionic compounds that are in a water solution. Okay. So then with that information, we can actually write a reaction from words. Also remember which elements are diatomic. Have no fear of ice cold beverage. Okay. So everything's coming together, hopefully. We get into chemical reactions. So we talked about the physical states of the elements, right? We talked about the aqueous solutions. We talked about the solubility, using solubility rules, okay, which would tell us either if a ionic compound is aqueous, AQ, or insoluble. Remember the solubility rules? Either you're soluble or insoluble. If you're soluble, then it's AQ. If it's insoluble, then it's S for solid. Okay. So those are the key points to remember. And obviously, we know, hopefully by now, we started learning how to put elements together. Okay. All right. Now, the coefficients, as I mentioned, tells us how many of those compounds or whatever formula you have. So 3HCO tells you you have 3 molecules of water, H2O, okay? 3 separate molecules. We don't change the subscripts. The subscripts are etched in stone now. Remember, that's the ratio between the elements to give us a specific compound. So here's a reaction here. Sodium reacts with chlorine to produce solid sodium chloride. Okay, well, let's start off. Sodium, well, obviously we need to find out the symbol for sodium, which if you don't know by now, hopefully you can look it up and you can see that that is Na sodium. Na is the symbol. What do we also know about it? Well, it's a metal, right? We also know, based on its position in the periodic table, that it's a solid. Okay. Sodium reacts. So the key word reacts tells us plus. So sodium reacts, which is plus, with chlorine. Now, I will put the symbol for chlorine. Now, what do we know about chlorine? It is one of the diatomic elements. And so Cl by itself would be incorrect because it's diatomic, Cl2. To produce or to give, the words produce or to react, produce, that means that's the arrow. Okay. Produce solid sodium chloride. So we know that the physical state of that would be an S in parentheses. We got to put sodium and chloride together. Notice we're using IDE as compared to INE. INE is the element, okay? The diatomic element right here. The IDE tells you I have the ion. And I know it's a -1 because it's in group 7 and it's going to pick up 1 electron. Sodium in ionic form is a +1. I know that because sodium is in group 1, has 1 valence electron. And it's a metal, so it would lose an electron and therefore give us a positive charge. So here are the ions that I'm going to be utilizing before I put them down together to write to give it its formula. It's a simple 1-to-1, 1 sodium, 1 chloride. And so the formula would be as follows, okay? So that is the reaction given written in yellow there. I'll clean my mess here in a second. And so let me rehash it, okay? It's sodium, taking sodium, right? They didn't say sodium bromide, sodium, it said sodium by itself. That's the element. So that's Na. Reacts tells us that's the plus, okay? With chlorine, the fact that we're looking at INE tells you that is the element. And we also know that it is diatomic. So it's Cl2. To produce is the arrow. You also see it to reacts to give, or gives is another term used. That's the arrow. And then we get in, so anything following that term produce is product. Solid they're telling you that's the physical state. And then sodium chloride is the final product. Before we write the formula give it the formula, write the ions first, just like we did when we were doing before writing formulas for ionic compounds. We write them in ion form first, so we know how many of each to put together. So we know here sodium is a +1, chloride is a -1, simple 1-to-1, and there we go. We got the product. And now we got to balance it. So we write the formula, and we balance it. We got 2 chlorines in reactant side, but only 1 in the product side. So if we put a 2 there, that definitely would take care of the chlorides, 2 of them. They're balanced, but then I got to run back and put a 2 in front of sodium because I kicked up my sodium count. So basically, when we're balancing, we're doing this. We start there to go to reactants, or then we go back to products, and we go back and forth, okay, until everybody's balanced. And we don't have to start as reactants. We could start as a product and do the same thing. But 9 times out of 10, you start on one side, then you got to go back to the other side, go back and forth, okay? So that's our first step. Like I just did it by hand. Then we added the states, okay? And we know here that the formula for sodium chloride wouldn't be NaCl, right? Because we know the chlorides are -1 and the sodium's +1. That would infer sodium Cl2, this formula here, that would infer that sodium is a +2 metal. And that's not the case because we know that sodium is in group 1. All right. And finally, we balance it. And so here we have a perfect example of a very hazardous metal, which is sodium, hazardous and very reactive. And right here, and then a very poisonous gas. And we end up making something that we can very easily put on your French fries and not cause much of a problem unless you got high blood pressure and you're going to deal with the sodium content. Okay. And the only thing that happened there was a transfer of 1 tiny electron from the sodium to the chlorine, okay, to create the chloride in the sodium ion. Okay, so let's continue. Here's one. Aluminum reacts with bromine to produce solid aluminum bromide. So let's break it down. Aluminum. So we look the symbol up. We know that aluminum is Al. We also know it's a metal and it's a solid. Okay. So that's the formula for aluminum. Aluminum parentheses S. Reacts means we got a plus with a bromine. Notice the term bromine. As the case with chlorine earlier, the fact that it's ione tells me that we are dealing with elemental bromine, which is again diatomic. Okay. And do anybody know the physical state of bromine? Let me see. Yes, that is correct. It is a liquid. Okay, so LQ. Now, produce is the arrow. We got solid again. So it's a solid material. And then we have aluminum. Note the term here, bromide. Okay. And so let's first write them in ionic form first before we put them together. So we know that aluminum in ionic form has a +3 charge. Okay. And we know the bromides, as the chlorides, each have a -1 charge. And so we're going to need 3 bromides per 1 aluminum ion. So our formula will be AlBr3. Okay. So we got the formula now. We got the reaction. We got the aluminum solid reacting with bromine liquid to give us aluminum bromide. Now we balance it. Okay. Note here. Let me change the color to kind of separate a little bit. We have 3 bromides here and 2 there. So we find a common factor. What if I put a 3 there and a 2 there? That balances the bromides. Okay, 6 common number, which then kicks up my aluminum to 2. So I go over here and put a 2. Okay, so now it looks balanced. Let me clear this up a little bit. And there, 2, 3, and 2. And now our ratio is 2 aluminum, 2 atoms of aluminum require 3 bromine molecules. Okay. To react, when they react, they will produce a total of 2 aluminum bromides. And so let me draw those out so you can see what's happening there. Okay. So I need 2 aluminums. Okay. Which then react with three bromides. Okay. Which then gives us, this is better Br, and then aluminum here, Br, Br, Br. It's kind of messy, but you could see that, right? So I get my 2 aluminums, then a total of 6 bromides, and we're balanced. But we put the coefficients there because obviously we're not going to draw them out each time. So our coefficients are put in front of the reactants and the products to tell us how many of each we have. Okay. And now we have a ratio that keep track. Don't forget the ratio part. Okay. So that means I can write a ratio of 2 aluminums per 3 bromides in that form. Or I can write it in the form of the bromides on top. Okay. You might say, well, what is that? How does that help me? Okay, well, let's think about this. If I have 20 bromines, how many aluminums would I need? Okay. And so here's the problem. If I start off with 20 bromines, I need a conversion factor here. I need to figure out how many aluminums. So I need to write it so my bromines cancel out, right? Well, isn't that this one right here? With 2 aluminums on top and 3 bromides there. Okay, do not my bromides cancel? Give me the units of aluminum. Now it's 40 divided by 3 to tell me how many aluminum I have. So you see how that's set up, just like we did way back when with the conversion factors, keeping track of my units. Because eventually we're going to be using, like we did in the conversion factors, at least 3 conversion factors to get from point A to point B. And keeping track of your units by setting them up properly will get you to that point, okay? All right. All right, here's your ratios. I just put those in there. And I just used the ratio between reactants, but the ratio between reactants and products are also, you have to keep a track on, because you could be asked a question about aluminum versus, if you have 10 aluminums, how many aluminum bromides would you get? Well, then the ratio between aluminum and aluminum bromides is a 2:2 or a 1:1. So if I have 10 aluminums, I'm going to get 10 aluminum bromides. Okay. All right. So, all right, here we go again. We got the reaction of phosphorus reacting with oxygen to make solid diphosphorus pentoxide. Okay. All right, that's a good one here. Let's break it down. And so what I have is phosphorus, which is the symbol P. Okay, and also is a solid. Reacts with oxygen. And I know that oxygen is diatomic and it's a gas. Okay. So here we have reacting. Phosphorus reacting is our plus with oxygen to make is our key for the arrow. To make diphosphorus pentoxide. Okay. So here we are given the name, we want to write the formula. And if you recall, for this covalent compound, my first suggestion was to write the parent formula first. Phosphorus and oxide, HSPO, okay? And then we put in the prefixes. So di is 2 and penta is 5. And so we have the formula diphosphorus pentoxide, solid. Okay. And go back and check. Okay, does what I wrote, what I put down, is it consistent with what is given? And the answer, let me write that. Let me change my pen color. Yes, it's true. We got phosphorus reacting with oxygen. Okay, that checks, reacting, that checks, to make is our arrow, solid, that checks, diphosphorus, pentoxide, and net checks, the formula, okay? So the formula is written, good, now we got to balance it. Check this out. We got 5 oxygens over here, 2 on the reactant side. Guess what? We can use the same kind of little aid there to help you. We find a common number, which is 10. So I can put a 5 right here and a 2 right there. My oxygens are balanced. I got 10 on each side. That does kick up my phosphorus to 4, so no problem. I put a 4 in front of P for phosphorus, and I have a balanced chemical reaction. Okay. Let me clear the mess, and we'll use the slide. Okay, here's the formula we just wrote down, and we put the physical states, and then we balanced it. Okay. Now let me ask you a question here. If I start off with, let me see, 20 oxygens. If I have 20 molecules of oxygen, got 20 of these, okay, O2. How many phosphorus do I need? Okay, well, to answer that, like we did with the problems of conversion factors, you write down what you have, what you're given, right? We're given 20 oxygens. Obviously, we're going to need a conversion factor here, right? And what are we looking for? We're looking for phosphorus. How many phosphorus we need? So starting with 20 oxygens, obviously we need a relationship between oxygen and phosphorus because I want phosphorus in the denominator and, oxygen in the denominator and phosphorus in the numerator. Why? Because I want my oxygens to cancel out when I do the math, unit-wise. And so I come back to my balanced chemical equation. I know there are 5 oxygens per 4 phosphorus. That's the ratio. Okay. And so now I have the answer would be what? 16 phosphorus. Right? 20 times 4 divided by 5 gives me 16. Okay. And this number that I set up is true whether I use 20 oxygens or I use 20 billion oxygens. It's the same ratio. Okay. Same ratio. All right, let me clear the table here. Here's a bit of challenging one, but don't let it freak you out. Break it down stepwise. Okay, a lot of these problems, yeah, they look overwhelming. But break it down. Okay. What we have up here is nickel 3 sulfate plus lead 2 nitrate produces nickel 3 nitrate and solid lead 2 sulfate. Sounds all confusing here, right? No problems. Let's break it down. Break it down to the ions first. Let's do the first one, which would be nickel 3 sulfate. Well, remember that Roman numeral tells you what is the oxidation state of nickel. They're telling you that you are using nickel. Whoop, where's the mouse is going crazy here. You're using nickel plus 3. Okay. And the sulfate is, well, where do I go? Remember the polyatomic ions? That's the sulfate. Okay. And so now I got the sulfate and I got the nickel. Now I can, look at it. Remember the little cross cross number wise I talked about, or use a common number because I got a +3 and a -2. That means my common number would be 6. So I need 2 nickels and I need 3 sulfates. So my formula will be nickel 2. And since I need 3 sulfates, I need a parentheses. Remember the polyatomic ions, when you need more than one, you put a parentheses around it, then you use the subscript to tell you how many of those you need. So that is a formula for nickel 3 sulfate. Okay. Plus tells you that's the plus sign, obviously. But now we got to do lead 2. Well, lead 2 is the +2. And the nitrate, go to the polyatomic ion table. You'll find that to be NO3 -1. Okay. And so I need 2 nitrates for every lead 2. And so lead, I need parentheses, NO3, 2. Okay. So those are the reactants. All right. So let me change the color here so we can keep things separated. And then produces is the arrow. And so here it says nickel 3 nitrates. Okay. Again, break it down. Nickel 3 nitrate, which is NO3-. Okay. And I need 3 nitrates for the +2, 3 nitrates, because there's each one's -1, and the nickel ion you're using is a +3. So its formula would be Ni, I need a parentheses, NO3, 3. Okay. Then finally, solid lead 2 sulfate. So again, we're doing with lead 2. Okay. And sulfate, which is NoSO4 -2. And guess what? It's a +2 and a -2. It's a real straightforward 1-to-1. Plus, it's solid. Okay. Now, what about the state of the others? Well, guess what? They're telling you, they're giving you a hint here. They're saying aqueous reaction, so it's a water solution. So what do is you go to the solubility table. Okay. The solubility table will tell you that the nickel sulfate here is soluble. Okay. The lead nitrate, remember all the nitrates will be soluble, so it's aqueous. And again, the nitrates again are soluble. Okay. So these 3 here, as far as the physical state, you will get from the solubility table, but they gave you a hint right here. They're saying aqueous, so those guys are all aqueous. Then they told you what the solid state is here, solid. This, by the way, is an example of one of the 6 reactions we're going to talk about. Okay. All right. So we have the product. We got the reactants in red and the products in yellow. Okay. So now I can just put all that together. Let me clear the table here a little bit. Use and you end up with that. Okay. Now, balance these are, this particular one is called a double displacement reaction. This is one of the reactions we're going to talk about. But notice the 2 reactants are both soluble in water. Okay. And when you put them in separate containers, beakers, test tubes, 9 times out of 10, they're clear liquids. No color on them. Some of them do have a little color, but they're clear liquids. The moment I put them together, they exchange partners. Okay, what do I mean by that? Well, let me, the nickel combines with the nitrate, and the sulfates combine with the lead. Okay, they essentially exchange partners. Now, in the process of doing that, because remember, these guys are in solution to begin with, and they can very easily bounce together with the opposite partner. If they get together and they are insoluble in water, guess what happens? They precipitate, because we know that lead sulfates are insoluble in water, and you get a powder, and it precipitates and it gets cloudy. Okay. In fact, this is one way to test for lead. You got a solution that causes a precipitate, and that's a good indication that you have a lead or one of the heavy metals at least. Okay. Now, with respect to balancing these reactions, follow the polyatomic ions. Balance them out. Okay. Follow the poly. See here, we got 3 here with the nickel sulfate. Okay. That tells you that I'm going to need 3. Let me draw this out. I got 3 nickel sulfate, excuse me. I got 3 sulfates. Well, the product I'm going to make is I'm going to need 3 of them. So to balance those sulfates, I simply put a 3 there. It kicks up my lead to 3. So I put a 3 with the lead nitrate. Okay. And it by default gives me 6 nitrates, which then the final thing to balance are the nickel nitrates, which there are 6 by default that fall in at the end. So remember this part, when it comes to these type of reactions called double displacement reactions, okay, to balance them, follow the polyatomic ions to get them balanced, okay? The first 2 examples were mostly trial and error, but here you follow the polyatomic ions, you should not have a problem. It'd be a lot easier to balance them. One second, something's dinged here. Okay. Clear this up. All right, so here are the 6 types of reactions. Now, they've been written in generic form by using the letters A and B, maybe some other letters in here. Okay, to get you to kind of first think of these reactions in generic terms and then apply them to chemical reactions. All right, the first one is called a combination reaction, and by definition, it defines itself. You have A and B. 9 times out of 10, A and B are elements, and they come together to form some new compound, AB. Okay, 2 different reactants coming together to form one product. Okay, guess what? The opposite of a combination reaction would be a decomposition reaction. In this case, they're using something ABC, some complex compound, but they decompose back to the respective elements, A, B, and C. In other words, you start off with one product and it breaks down to give you a multiple of, you start with one reactant and you break it down to form a multiple of products. Baking soda is a good example. If you heat baking soda, it will break down to either carbon dioxide and a salt. Okay, so combination brings them together, decomposition breaks them apart. Combustion reaction. Now, we're only going to be concerned about one type of combustion reaction, and that is combustion reaction that deals simply with what are called hydrocarbons. And that's what these guys right here are. Hydrocarbons are essentially compounds that have nothing but carbon and hydrogen. That's it. The gasoline you use to combust your vehicle, the majority the material that's there that burns is hydrocarbons. They're made up of nothing but carbon and hydrogen. So they vary in X represents a number. The smallest number X is 1, and the smallest number of Y, subscript Y, is 4. So CH4 is the smallest hydrocarbon we're aware of, and that's called methane. Okay. I mean, you can vary, you get higher. The next one is you have things like butane, propane, nothing but carbon and hydrogen compounds. Now, one of the key ingredients of any combustion reaction is oxygen. Nothing burns. We all know that. You can't make a fire without oxygen. So automatically, when they talk about a combustion reaction, think oxygen is one of the reactants. Okay. Now, for Chem 130, when we do a combustion reaction, the only two products that you will obtain are carbon dioxide and water. Okay, carbon dioxide and water. Now, obviously, the hydrocarbons that we burn in our vehicles do not give pure carbon dioxide and water because our engines are very inefficient, and our system to burn hydrocarbons is very inefficient. And therefore, we do get carbon monoxide coming out of the exhaust of vehicles. Okay, that's because of the inefficiency of our engines not burning it correctly. And it also produces water. So sometimes if you're driving down the road, you see somebody's tailpipe liquid coming out. What you're seeing is basically water coming out, water that has condensed, because it's normally so hot, it's a vapor. Okay. And so two things about combustion reactions, right? One, oxygen is a reactant. Two, the only two products you can obtain are carbon dioxide and water. That's it. And the hydrocarbons consist of some carbon hydrogen entity. There's carbon and hydrogen by itself. And we also have a stepwise method to balance chemical reactions for combustion reactions. They're stepwise. We'll get to this. Okay. We spoke about acid-base with a chapter of acid and bases. Remember that an acid is by definition, anything that produces a proton, H+. And the base is anything that produces a hydroxide ion, OH negative. When those two combine, you get water. Okay? Water. Proton, hydroxide, always gives you water. That's a neutralization reaction. It's an acid-base reaction. Okay? And then the corresponding salt, which depending on what anion you use, this could be chloride, it could be any anion, and then whatever metal is used, you form the corresponding salt. Okay, that's your fourth type of reaction. And all right, this one here is called a single replacement reaction. Now, in order for this to, we're going to be able to predict this. Now, how are we going to do that? I direct you to the infamous periodic table. Okay, get this out of the way. All right, right above the solubility rules was another table called list the activity series. Okay, the activity series. And the way you read this, if you look in the far left on the top row, you got two rows here, and labeled starting with lithium. Those really should be stretched out. They put them on top of each other. And then you got the greater than symbol. So lithium, as far as activity, as far as reactivity, lithium is more reactive than potassium, and potassium is more reactive than barium, and so on until you get to the end of the list where gold is the least reactive metal there. Okay. Also notice something interesting. H, the way this activity series works is in reference to hydrogen. Okay, reference to hydrogen, which could be in the form of hydrogen gas or water. Okay, so that's the reference point. So now the ones that are highlighted and have underlined lithium, potassium, barium, strontium, calcium, and sodium. All that means is because they're in bold and underlined, that means they're so reactive that you put them in water and they just erupt. Okay, in fact, you have to store them in like an oil, mineral oil, because they cannot react. They cannot be put in water. They react explosively. If you were to take a chunk of sodium metal and dump it in a little pond, it will bubble up and a lot of heat given off, and it will ignite because of the hydrogen that's given off. Obviously, it won't ignite in the surface, but on top of the surface, it gets pretty warm. All right, so that's the activity series. So we're going to utilize that activity series when we talk about these type of reactions called single replacement reactions. Now, if you look at this generic formula, you can see that we have a metal in elemental form. Okay, so we have M in elemental form, and then we have another metal that is in salt form. Okay, that's what the X represents. So it could be something like sodium chloride, okay, or some salt, some ionic compound. Now, depending on the reactivity series, the two metals exchange places. So the M now is bonded to the X to give you MX, and the A that was in ionic form now is back to the elemental form A. Plating is a very good example of single replacement reaction. When you're plating silver, you're plating copper, you can plate all kinds of metals. That metal, that chrome, for example, that metal that is plated on the surface of some material is an example of a single replacement reaction. The metal that you want plated is in salt form to begin with, and then exchange places with the other metal. Okay. All right. And then finally, the double replacement reaction, okay, which is an example of what we just did with the nitrate and the sulfate. Remember that one? Notice here we have two reactants, two different metals given subscript 1, subscript 2. Okay, that's what that means. It doesn't mean there's two M's. It means two different types. All right, so let me color that. Let me emphasize that. Make sure we understand. So we have this metal, M1, one type, okay? And then we have this metal right here, a different type. Oh, yes. Yeah, we got 1 minute. Thank you. Appreciate it. And so what's happening, if you look carefully, the M1 type now is exchanged and now partnered with the Y. You got M1X, M2Y, okay? They react, they exchange partners. One of these guys will be insoluble based on the solubility rules, and we'll get a solid, and you get a reaction. If both of these final products, new products, are soluble in water, there's no reaction. Remember that part, okay? So in this case, for double replacement reactions, we utilize the solubility rules to determine whether we get a reaction or not. Single replacement reaction, we utilize the activity series to determine whether we get a reaction or not, okay? All right, well, let me stop it here. We are on slide 11, and we will continue on Thursday. And, oh, okay, hello, and welcome back. I'm glad everybody's back. Our exam has 156 points. Whoa, that's not right. I need to check that out. It should only be 100 points. There's only 22 questions. Let me find out what happened there.
There's 42 questions.
42?
Mm-hmm.
Something's not right.
If we already took the test, do we have to retake it?
No, let me go take a look and see what's going on. Something's not right. No, because if you took it already, and I'll use your percentage. Let me find out before I say anything. I don't know what's going on. Okay, because in fact, I checked it earlier today and it was 22 questions. So. All right. Okay, let me find out. I'll get an email out ASAP. Okay. All right, guys. You guys take care.